So in this lecture video, I am going to be covering one of the first ways that you actually measure the concentrations of aqueous solution. So again, recall that aqueous solutions is when a soluble solid or a miscible liquid is dissolved in water. That is actually the definition of an aqueous solution. So the first example of how you measure how much solute is in water solution is this little unit called percent volume. And percent volume can also be expressed as mils over mils. And the formula can be expressed more thus. Okay, it's the mils of solute. So in this case, we're talking about the mils of the liquid solute over the mils of the total solution. And the mils of the total solution is always going to be the mil of the solute plus the milliliters of water. So the volume of water in this case, times 100. That's why it's a percent. It's because it's a division followed by a multiplication by 100. Part, smaller number, whole, bigger number, times 100. How do you know you're going wrong with a percent, volume, percent, or whatever percent calculations? If your percent calculation is above 100%, you have went wrong somewhere. Okay. Now I say in this video that this is the measurement of the mils of solute, which is the liquid. But you also have to remember that you can convert the mils of a solute, in this case, into grams of solute, and vice versa, using the density equation, and that's going to come into play later. But first things first. So here's an example. So again, in this case, the percent volume is the mil of solute over the mils of solution. So if you have 23.6 mils of ethanol dissolved in 56.6 mils of water, what is the percent volume of the solution? So this is the solute, this is water. That means to say that you have to do an addition first in order for you to actually get the total volume of the solution, which is 56.6 mils plus 23.6 mils. So 23.6 mils divided by the sum of the solute plus the water times 100 is actually 29.4%. Where did I get this 29.4%? Why do I need 29.4%? The given numbers is actually in 3 significant figures, and this has also to be in 3 significant figures. Right? So when you see water, be cognizant that that means that there has to be an addition that you have to do. That is shown in this denominator here. Another example, what is the percent volume of the solution when 45 mils of ammonia? Ammonia, by the way, is soluble in water. Is dissolved in 320 mils of solution. So in this case, there is no addition required because the solution, the total volume of the solution is given to you. Here it says water, here it says solution, here there's no addition, here it says water, there was an addition. Okay, so again, part over whole times 100, that gives you 14.0% ammonia. Again, note here that the percent volumes are all lower than 100%. Again, if you came up with like a number that's like 163%, note that you have done something wrong again. Right? There are some variations with this example. So in the previous 2 examples, we have calculated the percent volume. Right? But you can also go from percent volume to the mils of solute or the mils of water if needed. Okay? So here is a variation. How much ethanol is in 500 mils of a 10% ethanol solution, and in this case percent volume ethanol solution. So anytime you see a percent unit given to you, you need to understand, and I hope that you remembered for your mathematics, that a percent is always a number divided by 100. Right? So this means to say there's going to be 10 mils of ethanol in 100 mils of solution. 10% means 10 over 100. If this was 5%, it would be 5 over 100. So this is the total solution. So what you do is a dimensional analysis problem. And what you're trying to do is you're trying to get rid of, in this case, the solution. And guess what happens if you go 500 ml solution times 10 mils ethanol divided by 100 mils of solution, the solutions cancel, and the unit that you left behind at the end is actually mils of ethanol. And that is actually how you get, so in 500 mils of a 10% ethanol solution, there's actually 50 mils of ethanol in that whole solution. Okay, that should make sense, because 10% means for every 100 mil, it should be 10 milliliters of ethanol. If it's 2%, that means it's every 100 mils of solution, there should be 2 milliliters of ethanol. All right. Another variation is trying to find how much water is actually in a solution. So here we go. How much water is in 200 mils of a 5% volume ethanol solution? Again, the first step is similar to what you've had before. So again, the mils of solution cancel. Anytime you see percent again, note that it's 5 over 100. And what is the number on the bottom always? Always the mils of solution. Okay, so 5% means that for every 100 mils of solution, there's going to be 5 mils of ethanol. So it should make sense that in 200 mils of solution, you actually have 10 mils of ethanol. So that's the first step, because the whole question says how much water. So we do not have water yet, we only have ethanol. However, if you see it, we actually have 200 mils of solution. Out of this 200 mils of solution, we actually have 10 mils of ethanol. So if we do the subtraction, out of the 200 mils of solution, 190 mils is actually water, and the remaining 10 mils is actually ethanol. So if you want to go home and you want to make a 5%, I know it's most beers are actually around 5% ethanol, all right, the light beers, okay? So if you drink a stout or something like that, it becomes a little bit more higher. What you just need to do is you just need to take 10 mils of ethanol and pour 190 mils on top of water, and then there you go. You have in this case, an alcohol content similar to beer. I don't suggest that you do this at home, obviously, because I think that's illegal. All right, everyone. So in the previous slide, we've talked about percent volume, which is mils of solute over mils of solution. So in this slide, we're going to be talking about percent mass volume, or grams over mils. And it's going to be the same thing. It's going to be the grams of solute. Solute is always going to be on top, and the mils of solution on the bottom. And again, the mils of solution can be broken into a separate calculation, which is the milliliters of solute plus the milliliters of water. Okay. So we might as well do an example. What is the percent gram per mil, which is the percent mass volume, when this much sodium chloride is dissolved in this much solution? So in this case, we don't need to do any addition to find the number for the denominator, since the solution is already given to you. So it's just going to be straightforward. This, which is the grams of solute, over that times 100, which is the volume of solution. Right, and that's how you get 5.50 grams percent sodium chloride. Now, just as an aside, anytime you see a percent composite, or in this case percent concentration, make sure that you indicate what percent concentration you're talking about. Is it volume? Is it mass volume? Is it mass? Okay, because that is actually another way that you can do that. The other thing that you can think about is you look at the substance that's being dissolved in water, and you just think to yourself, well, what state of matter is that at room temperature? And obviously salt, sodium chloride table salt, is a solid, so if this is not given to you, you can always assume that it's a solid room temperature. It's actually grams per mil. But just for our purposes, make sure that you indicate what percent concentration you're actually using. Right? So that's easy. This is a little bit more complicated. So it says, what is the percent mass volume when 23.5 grams of magnesium chloride is dissolved in 150 mils of water? Right? The mils of solution is the milliliter of solute plus the milliliters of water. However, the solute in this case that's given to you is actually in grams of magnesium chloride. So therefore, we need to convert this grams of magnesium chloride into milliliters of solute, milliliters of magnesium chloride, by using density, which I gave to you in this example. So again, just as a hint, if I give you a density, more than likely 99.9%, you will be using that unit or that actual number at least once during the actual mathematics. Okay, so the first thing is we need to convert this grams of magnesium chloride into milliliters of magnesium chloride, because we need to have a total volume of solution first, which is shown here. So I use this relationship. Now remember that this is 2.32 grams over 1 mil. So we take 22.5 grams magnesium chloride times 1 mil on top over 2.32 grams. And the reason why the grams is on the bottom is you want to cancel the grams and you want to end up with mils. And that's actually what we get, 10.1 mils of magnesium chloride. So now we have mils of solute. So now we can now figure out the total volume of the solution, which is 150 plus 10.1. So at that point, we can do a straightforward mathematics. Grams of solute divided by the total volume of solution, which is 150 plus 10.1 mils. This again, milliliters, is actually figured out by using the density. And we come up with 14.7% magnesium chloride mass volume. Variations, again, the variations are actually quite similar here for mass volume and volume. Here, again, we are looking for how much sodium chloride is in 250 mils of a solution if it's a 12% mass volume concentration. So it's a straightforward math. The mils of solution has to cancel out. Again, remember that anytime that you see a percent, it's always that number, and you look at the concentration. M, mass, is on top. That means it's going to be 12 grams over any percent will have a denominator when it's expressed as a fraction of 100. And in this case, the denominator is volume. That's why the unit underneath is milliliters. And that's how you should be able to cancel the milliliters of solution, right? And that's how we figured out that in 250 mils of solution, we actually have 30 grams of sodium chloride. Note, there are four significant figures here. There's 3 significant figures here. This doesn't count because this is an exact number, 100, 1, or 1, just 1. So in this case, this is why we have 3 significant figures for our answer. We're following the least significant figure in this case.